And I'll take you to practice quiz problem number 1. Don't get the integral, only approximate the answer. I'll give you another minute or so. Okay, 30 seconds more. Alright, so that's the inner integral. And so we see that y is between 0 and 2x, while x is between 0 and 1. So what does that mean for, and I'm just going to draw a simple 2 space. So x goes from 0 to 1. While x is at 0, the y goes from 0 to 0. While x goes all the way to 1, when x is all the way at 1, the y is going from 0 to 2. So, and as x goes at 1/2, the y is varying between 0 and 1, and so on. It's going between here and here. This is the region that we are integrating over. We sometimes call this region D, or R, whatever. And so then we're going to be finding the volume of the underneath the surface. And the surface is half of xy is 15xy squared. And since we're in the first quadrant here, we're going to be entirely within the first octant, and we're above the xy plane the whole time, or on the xy plane. And let me pick, now, the bigger the y is, that's going to impact things much more than x, because of that y being squared. And when you're up at 2 for the y, your square is 4. When you're at 1, the square is just 1. So you would think that these should have more, weight on them. They're going to influence you more. A point up here is going to influence the volume a lot more than a point down here. But there's a lot more points down here than there are up there. That kind of balances out as far as the y goes. So I think a representative point might be kind of halfway between, for 0 to 1 is 1/2, And then maybe somewhere up, somewhere up in here maybe. Maybe something like this. Now, what does the coordinates of that point look like? So one reasonable way to do it is to take one kind of midpoint and figure out this value and then use that as the estimate. Another way to get the height, an average height, would be take heights at a few different points, numerous points, and then just kind of observe from there. This is a little bit quicker where I can just take the height from one point. So that's what I'm going to do. And I'm going to take that f, if it's 1/2, that's 0.5. And then the height looks like maybe 0.75. I'm going to plug that in. And then that's 15 times 1/2 times 0.75 squared. And I'm going to punch that into my calculator. And I get 4 point, I have my pen upside down, 4.21875. Alright, so now we'll take the volume under the surface will be the area of D times an average height, average Z value, if that's Z. And the area, well, this is, if you had the entire rectangle, that's area 2, so it's half of that, so it's area 1. And we're going to use about 4.2 for the average height. So I'm going to come up with my estimate being about 4.2. Alright, so give me some feedback about, is it difficult for you to come up with estimates of area? I know students in the past, some have said, oh, this is the hardest part, I gotta just skip the estimating the volume because that's too hard for me. And others wind up, getting it more quickly, but some just, they take a while. But if you keep at it, you're able to get this. So that's why I want to emphasize this. So tell me how you are in getting an estimate. And you didn't have to necessarily get close to mine. Yes?
I'm sorry. So main point is you just pick the convenient point, point
somewhere
you
near
can
the center. Yeah.
Easy to find the coordinate.
Yeah.
Okay.
Somewhere near the center of the figure, so it's kind of an average height. Or I could pick a few different heights if I wanted to get, spend a little more time, maybe get a little better estimate. And yeah, I agree with you, Matthew. A lot of people find getting the exact answers easier. Okay. And okay, we're going to keep doing this, and we're going to notice that as we go on and take crazier and crazier integrals, and we are going to get some really crazy integrals coming up, the ability to estimate will be the thing, though, that grounds us, that gives us, oh, I understand what it means. And it'll be even more important as we move on. All right, so now go ahead and find the exact answer, do the integral, and then see how close we were with our estimate. I'll give you 30 seconds more. If you don't finish, that's fine. You can try to just stay ahead of me. So I'm going to do that inner one first, and the only variable is y, so it's y cubed over 3. Y cubed over 3. And then evaluate this, and all the constant part we don't need to evaluate from. Just factor that out. From y equals 0 to y equals 2x dx. And then this 5 will come out in front. The integral from 0 to 1. Now this x, although it's a constant relative to this, it's still got to stay to the right of the integral sign. And then when I plug in 2x for y, I get 8x cubed. When I substitute 0 for y, I get 0. Okay, and now I need an antiderivative. The 8 will come out front. 8 times 5 is 40. Antiderivative of x to the 4th is x to the 5th over 5. Evaluated from 0 to 1. And then that's 40 over 5 is 8. And then 1 to the 5th is 1. 0 to the 5th is 0. And my total answer is 8. And now it'd be nice if my approximation was closer, but it was 4.2. Now in a case like this, I might go back and I might figure out a few values. If I plug in, now let's call this z, so it's quicker. Z equals, here and here, you're 0. Where either one of these things is 0. All the way across here, your y is 0. So even at this point, z is 0. Okay, and then way at this point up here, z is equal to 15 x, which is 1, y, which is 4, y squared is 4, and then that's going to be 60. Oh, it's really tall right above this. So, although there's not so much of it, it does go way up there. And then let's take one more point over here. And that looks like it's going to be 1/2 and 1. If you plug in 0.5, you're going to get z equals 0.5 times 15. Oh, let me just, that's 7.5. Times y, which is 1 squared, which is 7.5. So it's 7.5 right up here, and 60 up here, and then down below it was, we found it to be 4.28 over here. But, so the area was 1, but the average height might have been even a little above there, somewhere, 8 instead of 7.5, because this is going up so high. And that seems reasonable to me. So I can drive this answer with that. Reasonably comfortable. Yes.
So that means we have to have a vague idea whether a given function is a smooth or the more curvy function.
That's right.
Or yeah, then that means to find that out when which case that is, then you have to plug in the certain endpoint and see the difference between each endpoint,
Mm-hmm.
and gives you a rough idea the where the average height might fall on the region.
That's right. And it's not important that we get this answer that close. It's just, I mean, if we'd have estimated 800 and got 8, then something's really off. Or if we say, oh, it's definitely going to be negative, but then it's positive, then we're really off. But, you know, when it's double what we estimated, that's not that big of a deal. And it also just helps us to kind of remind us of what this means. It makes sense of it. It makes the answer. You can tell if you did something really off. Most of the time, these are not going to be linear functions, and they'll be curvy. And but you know what? Just picking one central point and going with that is usually fine. You don't have to do the stuff that I did in black here. I was just, you know, spending more time than I needed to kind of justify why this was small. By that time, I'm a little bit curious. Why did I get such a small estimate? And that kind of answered my curiosity, because I was getting such a big number way up here. The height is so big. All right, so let's go to number 3. And this is a region D, just like the region D was the region mapped out by the intervals for the integral. Okay, the region D looks like this. Straight lines. This is the point 2 over 1 up. Okay, and so map out the inequalities that define this region. So I'm going to give you a minute. Fill in what goes in the left and the right of the x and the y inequalities. Okay, 15 more seconds. All right, the first thing I need to do is to decide, does this have a consistent rightmost and a consistent leftmost function? No, it does not. Because from 0 to 1, the rightmost is this vertical line above 2. But then the rightmost function is this slanted line. All right, so I would not do rightmost and leftmost. Does it have a consistent uppermost and lowermost? Yes, it does. So I can break it up into one region, and that's the way I would do it. And so the uppermost function, I need the equation of this line right here. Well, this is the line y equals mx plus b. Now the b is 2. And the m is it's going down 1 and to the right 2. Negative 1/2 x plus 2. So the x's One of these regions has to be all constants. We have an uppermost and lowermost, but this is not a horizontal line, it's slanted. So that's going to be the y's. The x's have got to be between 0 and 2. The y, meanwhile, has to go, now the y is 0 is the bottom, and then the top is this y right here. Like this. Okay, give me some feedback on number 3. Please. And number 4, same type of thing. This is the best way I could do a semicircle. So this is a top half of a circle. Okay, 30 seconds more. All right, the equation of the circle with radius 1, centered at the origin, is x squared plus y squared equals 1. And now this one, does it have a consistent rightmost and a consistent leftmost function? Well, it's the same function that's rightmost. Here is the rightmost and here is the leftmost. I don't want to do it that way. I'd rather have two different functions. And uppermost is this semicircle, lowermost is this line. So I'm going to solve for y. I'm going to get y squared is 1 minus x squared. I'm going to take the square root of both sides. And I'm going to get plus or minus the square root of 1 minus x squared. Now if I take the plus, this is the part of the semicircle above the x-axis, where all the heights are positive. If I'd have taken the minus, I'd add this region down here. Okay. So the y's are, so the x's have to go from -1 to 1. One of them has to be constants. The other one, while the x is traversing from -1 to 1, the y's for each of these, when x is -1, the y goes from 0 up until positive square root of 1 minus x squared. So when the x is -1, plug that in, you'd get the y being just 0 to 0. But as x moves to 1/2, you'd have the y going from 0 up until square root of 1/2, which gets you right up here. Alright, so go ahead and give me some feedback on number 4, please. questions? All right, if no questions.
Actually, I had a quick question. This is kind of like a clarifying one. So for number 40 from 16.2, it was with a semicircle. I just wanted to make sure that I drew the semicircle right.
16.2.
Number 40.
40. It's page 1024. Write an integrated integral for the continuous function. Okay. So we're supposed to write the integral. We don't have to evaluate the integral.
Yeah. And so would that look like a semicircle that was like if you took a circle and you split it by the y-axis? That was like my main question.
Alright, well let me read this slowly. It's the region in quadrants 2 and 3, bounded by the semicircle with radius 3, centered at 0, 0.
Wouldn't you sort of differentiate by the x-axis first and that have the x integral on the inside and then have the y integral on the outside?
I'm not. Let me finish drawing this and then I'll have you say that again because I couldn't quite process what you were saying. Alright, R is the region in quadrants 2 and 3. Alright, so that's the region R. Everybody okay with the picture on that?
Yep.
Okay, now Cameron, what were you saying?
Wouldn't we, for a double integral, wouldn't we have differentiate with respect to y on the outer integral and differentiate with respect to x on the inner integral?
Ah, yes. Because we don't want to do the upper function and the lower function. We want to do the leftmost and rightmost. So we want to set this up. If you're going to be setting it up like this, the region R. Now this corresponding to x and y constraints. Okay, so we want y to go from this time, these be constants. And we want the x to go, we take that same equation, except it's x squared plus y squared equals 3 squared, which is 9. But we solve for x. And we get x is equal to plus or minus the square root of 9 minus y squared. And this time we're going to take the minus to get the left half of this. Okay, so now we got to go in the correct order from smaller to larger. From x is negative square root of 9 minus y squared to x is 0. Here to here. And if you set this up as an integral, as Cameron's saying, which one comes first now, Cameron? The dx or the dy?
The dx is on the inside and the dy is on the outside.
And the dy on the outside, because that's got to be constants. And then this goes from negative to 0. And that would be how the integral would get set up. Matthew, is that all clear?
Yeah, I just wanted to make sure that I drew it the right.
Okay. Very good. By the way, when you evaluate integrals like this that are really symmetric, this one and the one above it, if this function was one like this, odd power, let's just keep it to one variable. And it's just an odd power. We'll hold it. Y. And that's all it was. So I could immediately see that this area is 0. Because I'm going to get exactly the same height over here, and all the y values are positive. And I'm going to get exactly the same height of the region, the surface above it is over here, but negative. And these two will cancel each other out. Everybody following that? Furthermore, if it was something like this.
I'm sorry, I don't get it. If that is a 0 and cancels out, how do we find the area or volume?
You probably don't need to find these areas. In this case, you'd only be interested in the integral. And if we can just take the shortcut and say, hey, that integral is going to be 0, then we're done. We usually don't need to find the area in the domain. Okay. And then, if it was y squared, an even exponent on the y, then we might do this. And double it. Because you're going to get the same values here and here. And these kind of shortcuts get done all the time to make it go a little bit quicker. Any other questions? All right, let's go to triple integrals. And so it's kind of a natural progression. We've just had double integrals. But you might be wondering, well, what in the hell is going to be the interpretation of a triple integral? A single integral, the geometrical interpretation is the integral a to b of f of x dx is the area under a curve. And we're familiar with that. The picture that corresponds with that is this kind of picture, And we're getting that area. All right, but I want to point out, this becomes the length of the line segment from A to B if the f of x was 1. Because if the f of x was 1, this becomes the integral from a to b of 1 dx. The antiderivative of 1 is x, evaluated from a to b. And then you substitute b, and you just get b minus a. And by the way, the other way to look at this is you divide the interval from a to b, you subdivide it, you partition it, and all these things. And then you get the heights. But if the height is 1, it's just 1, then the length from A to B is both the length of that line segment and the area of this rectangle. Because b minus a times the height of 1 is the area. So if this f of x is 1, we drop a dimension from area to length along the x-axis. Double integral. We're used to this. We just had this idea. This is a volume, and this would be the rectangle from A to B on the x-axis, C to D C to D on the y-axis. But, important, just like this one, this becomes an area of the domain of integration in the xy plane if f of xy is equal to 1. So if you replace this f of xy with 1, because remember, how did we estimate those volumes? You found the area of the base in the domain, and then you multiplied that by the average height. Well, the average height is the exact height of 1 all the time, and so you just get the area in the domain of integration. Alright, so now let's go to the interpretation of a triple integral. Well, this can always be thought of as an area. This can always be thought of as a volume. Triple integral can't always be thought of as something. It can really vary. Alright, so this triple integral, this becomes a volume. One dimension less, just like these other two, if the f of xyz was 1. This will become a mass if f of xyz is a density function. And so, normally you would use density to get mass. Like if I have 3 cubic meters of water, and I know that the mass of water is 20 pounds per cubic meter. I'm making it up. Well, I would just multiply 20 pounds per cubic meter times the 3 meters, and I've got my mass. Now, what if you have something that is a mismatch of materials, so it doesn't have a consistent density? So, it can be really heavy on one end and really light on the other end. And, then how would you find the mass? Well, we might come up with a density function. F of xyz is the density at the point xyz. Alright. And then we might get a crude estimate for the entire mass by saying, alright, let's just get the average density for the entire region and multiply it by the volume of the region. But then you get a better estimate if you subdivide it into, let's say, 4 pieces. And then even better estimate if you subdivide it into 8 different pieces, 8 different cubes that you're taking the volume of, and so on. And each of these little cubes, you're saying, all right, let's take the average density in that cube and multiply it by the volume of the cube. And then you sum them all up, and you're going to get the total, and you're going to get the exact answer if you take the limit as the number of partitions, number of partition boxes goes to infinity. All right, so it can be used for many other applications as well, including finding the center of the mass. You have, not only can you get the mass of it, but you can divide by, if you can imagine just right how you might get the center of mass. All right, and one more is if the function f is temperature, then you kind of are going to see this top function as weighting all the different pieces of the volume by their temperature. So if the temperature was 1 at every single point, then this integral in the numerator would be the same as the integral in the denominator. But if the temperature is 2 degrees at every single point, you're going to wind up getting twice as big of a quantity on the top as on the bottom, divided out, and you get 2, that's your average temperature. And if the temperature is varying all over the surface, you'll need this integral, and it'll get you some kind of a weighted volume, weighted by the temperatures. And the way you would estimate this portion in the numerator of this fraction would be taking the average temperature for the whole region, multiply it by its volume. And then if you divide it by the volume, you're going to wind up getting the average temperature. Alright, so these are some possible interpretations of triple integrals. Let's go to number 2. How is a triple integral defined? Okay, and this is taken from the textbook. So, in the double integrals, we took the domain was the xy plane, some portion of the xy plane, and then we had a surface above it. In a triple integral, the domain is everything in the x, y, z 3 space, and then these are parts of the domain. So each cube, like this one cube, is singled out over here. Now it has a volume, and if you multiply the different changes in x, change in y, change in z together, you get the volume of that. That's going to lead to dx, dy, dz. Right? And then you would multiply by, suppose this was like an object, and we had some kind of function that was representing the density. Then you'd say, well, what's the average? Or instead of the average density in that cube, you'd find the density of some point within that cube. And it might be the very center of the cube, or it might be the lower left-hand corner point of every cube, or the upper right-hand corner point of every cube. It doesn't wind up mattering at all, because we're going to take the limit as the number of cubes goes to infinity, and we'll get the exact answer. But you multiply it by a representative value in there. And then you're going to get this Riemann sum. And then we let this triangle delta represent the maximum length of the diagonals of the boxes. Alright, so this is as the maximum length of a diagonal of a box goes to 0, then you gotta have more and more boxes. The number of boxes will go to infinity. And then this will wind up, from this definition, which is just kind of 3-space analog of what we did in 2-space, you get this turning into this. So summation of all those representative point times each volume of each of these things. And then, again, the triple integral, we eventually turn it into iterated integrals. Okay, now this region D, notice if dx is the last one, then these have to be constants, a and b. And then if y is the next innermost, then y can be functions of x only, cannot be functions of z. And then if z is the innermost, z can be functions of both x and y. Now we'll see all this and it'll make more sense in the context of this problem. All right, we're going to do this integral down here, and notice that there's an unwritten 1 right here. Since f of x, y, z is 1, we'll be actually finding a volume. Now the volume we'll kind of figure out. What are we finding the volume of what shape? Well, we'll figure it out as we go. But in general, the outermost integral limits no variables are allowed. The next, only one variable is allowed. And then, at most, 2 variables are allowed in here. Alright, so let's figure out how to work this out. And this is going to become equal to, we just look at the innermost thing. And I'd probably put these integral, this was, textbooks doesn't put these things in here, but this is, since this is dx, this is x equals 0 to x equals this thing. Okay, so we need, now if we want to do these portions, you might do these little timeouts. Let's just isolate this part. This integral from x equals 0 to x equals y plus 2z 1 dx. We need an antiderivative of 1 with respect to x, and that's x. And then evaluate it from 0 to y plus 2z. When you substitute y plus 2z, you get that. When you substitute 0, you get that, which is y plus 2z. So this is going to take the place of this, which I'm going to call a. Alright, so moving to the right, then this becomes equal to the integral 1 to 4, integral from, now I'm going to put these values, y equals z minus 1 to y equals 2z, and then everything in here, a, got replaced with this. Y plus 2z dy dz. Now I'm going to put all my focus here. Now this is familiar territory. We've done these kind of problems. I'm going to call this B. And so my next timeout is, now I'm integrating with respect to y, so this integral is going to wind up equaling y squared over 2 plus 2zy. I found an antiderivative of this and of this from y equals z minus 1 to y equals 2z. Substitute the 2z in. I'm going to get 4z squared over 2 plus 2z times another 2z minus, and then when I substitute z minus 1 in, I'm going to get z minus 1 squared over 2 plus 2z z minus 1. And I'm going to simplify this down. This becomes 2z squared. This becomes plus 4z squared minus, and then all this inside here. Now, this becomes z squared minus 2z plus 1 divided by 2. So, let's keep this in brackets for a minute. I'm going to get 1/2 z squared. The 2's will cancel out here. Minus z plus 1/2 plus 2z squared, when I distribute this, minus 2z. So this one, I set it up to be kind of not too difficult of a problem. Like f of x, y was 1. And I'm just substituting these values in. But look how complex you get. These can be long problems. And so then I'm going to get, now this 1/2 and 2z squared makes 2.5 or 5/2 z squared. The minus z and the minus 2z makes minus 3z, and then plus 1/2. So that takes the place of all of that stuff. Okay, so equals 6z squared. Distribute the minus sign. Minus 5/2 z squared plus 3z minus 1/2. Alright, this, what's the timeout? And notice I didn't want to be carrying around those extra integrals on the outside. So the triple integral, this timeout strategy, I like it even more. So now let's keep going. Equals integral from 1 to 4. Everything in here, oh, this was b. Everything in here gets replaced by that. Alright, the 6z squared minus 2.5 is what? 3.5. So let me 3.5 is the same as 7/2. So combine those two into 7/2 z squared plus 3z minus 1/2 dz. And then I'm going to have this come down to here equals, I need antiderivatives of these. So it's 7/2 z cubed over 3. And and then plus 3z squared over 2 minus 1/2 z. All this from z equals 1 to 4. And then when I plug in 4, 7/2 times 4 cubed is 64 over 3 plus 3 times 16 over 2 minus, I plug in the 4, I get 2, and then when I plug in the 1, I'm going to get 7 6 plus 3 halves minus 1 half. And this is equal to, now, it reduces, this reduces, and I'm going to get 7 times 32 over 3. 7 times 30 is 21 with, I'm going to get 224 over 3. You all can check, see if I'm making any mental errors. Plus 24 minus 2 minus, and then over here, 3 halves minus 1 half is 1. 7 6 plus 6 6 is 13 6. And then I can pull out my calculator and put all this together, or divide this in and get it exact. Either way is fine. And I'm going to get some number as my answer. And let me just punch it real quick into my calculator. $94.5. So, I got an answer for this triple integral, 94.5. But what is it? Yes.
I have a question and one comment. The one question is when we deal with the double integral, we draw the region on 2 dimensions, an xy plane, and try to figure out the boundaries. Then this is actually a 4-dimension problem with the 3 variables. So if we want to see these boundaries, which I guess we have to figure out eventually by ourselves, then we have to actually draw the volumes and figure out all the functions for each axis or each variables.
Okay, a little bit of that, just a tiny bit.
Oh.
So let's look at this, because that was good anticipation. You're kind of getting into what I was going to ask next, which is, what does this 94.5 represent geometrically?
It's a mess, isn't it? It's a mess.
All right. Well, we knew since f of x, y, z was 1, we'll be finding a volume. So it's the volume. It's the volume of what? Well, we had all the different things. We knew that x, now look at this integral. The z went with the outer one. Z was between 1 and 4. So, let me come back over here. That was the outermost integral, and then moving inward, the y was between z minus 1 and 2z. then the x the innermost is between 0 and y plus 2z. Now, this becomes too complex to want to be visualizing this for me in 3 space. But a couple observations I can make is in this graph. Now, the z is always between 1 and 4, where, between those two heights. Okay? Now, the y with respect to the z, and then x with respect to 0, and but anyway, think of there being a couple planes in here. Okay, it makes sense that we got a positive volume, not a negative volume. Positive volumes, since this represents a volume, would be above the xy plane. When you dip underneath the xy plane, you're getting negative. So we got some positive volume. Now, the other parts of this, no, it's going to be it's not going to be worth the effort to try to visualize all this. When it's easy to do, sure, I'm going to visualize. When it was easy, double integral, I could go back to the xy axis in a very comfortable way. Put the x horizontal, the y vertical, and I can draw that and so on. Here, when the visualization in 3 space is so much more difficult, we don't always have to do that. All right, we are at a break time, so let us start again. At 6:49 p.m. Anybody need to speak with me individually before I take my break? Nice to have you, Yulia.
Yes, I'm here.
Okay. All right, let's start up again. And any questions before I head on?
Just a comment. So we will have this problem on our exams and next days and the final as well. Do we have enough time to solve all these problems?
So the number of,
Previous,
yeah, each
So
one can be kind of long. So yeah, the number of problems that get assigned gets reduced because yeah, I can't expect you to do tons of these. But the technique you have is kind of, you've already kind of established it with the by doing the double integral. So it's a pretty logical extension of the techniques you learned with the double integral. All right, D is the region in the first quadrant bounded by this surface and the coordinate planes. Describe D with 3 inequalities. So I'm going to have you work on part A independently and take your best guess as to inequalities that are going to help you describe this, and then I'm going to have you input that into your group chat, and we'll go look at these ideas. Before you start that though, let me just give you a rough idea of the shape that we're looking at. So X, Y, Z. All right. At 9, this is the highest point on the surface. Come on. It requires me to put a bigger 9. All right. And that occurs when X and Y are both 0. Because X and Y be anything else, it reduces the size of Z. So it's parabolic in this direction. When you get to X being 3 and the Y being 0, the Z will be 0. So it's going to come down and hit here at 3. And it's also going to come down and hit here at 3. And in here, you're going to have a circular intersection with the XY plane. Now this probably should come more like this. Okay. And so this kind of falls back over here as well. This part that you can't see, it's falling back on this. It's kind of a cone, like a dish, and maybe a bowl that you have that's turned upside down like this. So describe D with 3 inequalities. Go ahead and start working on that. whatever ideas you're getting about this, type them into your group chat. And so that we all get kind of on the same wavelength, I'm going to have you all start with this. One of these, x, y, or z, has to just be constants. Now, this is just in the first octant. Oh, so those parts in the background here really are going to be gone, because it's just, you know, where x and y are both positive directly above this. Alright, so the x, when you set up the triple integral, the outermost one has to be just constants, and let's agree, it could be any one of these, but let's just agree that it'll be x. So then you all are going to come up with the y and the z. And we'll do it in such a way that we can then convert this right into a triple integral on this surface. Okay, 30 seconds more.
Are we using these inequalities to describe the bounds of the triple integrals, or are we using these inequalities to just describe
Yes, these will be the bounds on the triple inequality. The triple inequality, we don't know this function. It'll look like this. dv for now, but we're going to change the dv into dx, dy, dz, but not necessarily in that order. Okay, and this is, d is the region in this, that, remember we use like a capital D for the region in the domain that we're integrating over. And that in double integrals, that was a 2-space area in the xy plane. Now it's in 3-space. Okay, and let me ask group 1, any ideas for these inequalities?
Yeah, let's see. We both agree that the inequality for z is going to be greater than 0 but less than 9, or like, you know, with the equal greater than. So yeah, from 0 to 9 basically.
0 to 9. Z.
And okay, then for like the x, I thought that it's from 0 to 9 minus y squared. But we also have another option for the x, which is from -3 to +3. And
So you aren't using this 0 between x and 2 x.
yeah. And my reasoning for that is, like, if we're thinking about it, like x, if we're trying to evaluate the, I guess the z value, like if we move along the y-axis, x is always going to be 0. So we can simplify the z equation to just 9 minus y squared. And that's kind of like, that's what I think
All right,
yeah.
so go back to your x. What do you have an x?
From 0 to 9 minus y squared.
And how'd you get 9 minus y squared?
well, I'm kind of like looking at the circular shape that it kind of cuts out right there.
On the
So,
XY plane, right?
yeah, so as you move along y, the x is always going to be 0. So I kind of like eliminated the x variable. And since we're trying to kind of solve,
Well,
like,
no, if you're on
um,
this XY plane, as you move along Y, the X is going to be changing. The X was 3, but as you move further and further, the X gets smaller and smaller.
but isn't it, yeah, okay. I might be wrong. It sounds like I'm wrong, but.
Okay.
Yeah, I got it wrong too.
I just missed the point that it was a first octant, so but definitely minus the 3 parts that I initially thought they should change into 0 at least.
Okay.
I thought Ron was onto something with his bounds. What if we took the square root of 9 minus y squared?
All right. And where are you coming up with that?
That would describe, that would accommodate the, circular motion of,
Yes. All right.
of, um, of
On the
yeah.
XY plane, we'd like to know the shape of this dotted curve. Now, when you're on the XY plane, you're on the XY plane because z is 0. Let's go back to this equation and substitute 0 in temporarily. 0 equals 9 minus x squared minus y squared. Or bring the x and the y squared to the left-hand side. X squared plus y squared equals 9. It's a circle. Circle of radius 3. It would go all the way around except we're stuck in the first octant. Alright, now if this would be right if there was a square root around this. But let's stick with what I had first suggested, which was let's have the x go from 0 to 3. And then if the x has got these bounds, so this is going to be I don't know what's going to be here, d something, but I know this last one's going to be dx. So this will be x equals 0, x equals 3. And that's showing right here. Alright, and then if we confine ourselves to being on the xy plane, so we're kind of in familiar territory with x's and y's, and then we're, comfortable with this equation. That's the equation of a circle in the xy plane. And then let's figure out the bounds on the y then. So we'll solve this thing for y. And you bring the x squared to the other side. Y squared is equal to 9 minus x squared, and then you square root both sides. Now you'd put a plus or minus, but we're only going to take the plus part because when y is positive out here, now y being plus would give you the semicircle that would keep going on this half over here, but we can stop this from keep going by just having the y, the x, not go from 3 to negative 3, but from 0 to 3. So it just gives us this portion. So y is going to go from 0 to the square root of 9 minus x squared. So So before I move on from this, let me just describe again. We're going to have x be 0. While x is 0, the y goes from 0, while x is 0, plug it in, and y is going to go from 0 all the way up to 3. Now as x gets bigger, suppose x is 1, we've gotten out to here. Then the y, while x is 1, is going from 0 to the square root of 8, which is way out here. And so on. And as when we get all the way to x being 3, the y is going to go from 0 to 0 because it doesn't have any room to run right over here. This is going to map out, these two is going to map out this portion of this circle, 1/4 of the circle. It'd be 1/2 of the circle if we went from -3 to 3. It would be the back side of this circle if this was a negative sign in front of that. Is everybody okay with this?
Is it true that you could also just like do it kind of like the other way around though? Like have y be from the one from 0 to 3 and then x the yeah, okay.
Y could have gone from 0 to 3, and then the x would have gone here to here. That would have worked just fine too. Okay? And then, does everybody agree that if these two are set, that the z just goes from 0 to 9?
I don't know. I feel like I'm not understanding why the top one can just go from 0 to 3 because I feel like that would form just like a square base or because I don't know.
It does go from 0 to 3, and if the y was also going from 0 to 3, yes, you get this rectangle. But as x is going from 0 to 3, look at the x as being 0, and the y goes from 0 to 3 when x is 0. When x is 0.1, it goes from, y goes from 0 to really close to 3, but not quite, and so on. And it winds up mapping this out. It's kind of crazy. But this part right here, nobody's complaining about this, and you should be. If we left it like this, we would not be getting this shape. We would be getting a cylinder. Do you see that? This z is incorrect. It would just take this area and just send it straight up. All the points in here would be valid, and the z values for each one of these points would go from 0 all the way up to 9. So this is wrong. So let me undo those. And what does this have to be instead of 9? Anybody have any ideas?
Would it just be the function itself? 9 minus x squared minus y squared?
9 moved me here. Minus x squared minus y squared. So when you're at a particular point, the x and the y region has already been defined. It's inside this quarter of a circle. Take any point in that circle. If x and y are both 0, then you're at the origin. And then the z can go from 0 to 9. But if you're way out on the edge, suppose x is 3, and you're over here, and y is 0, z would go from 0 to 0. It doesn't get any height because we're way at the edge. But if x is like 1 and y is 1, then we'd be at this point right here. And then you'd go up close to 9, but not quite. You'd go up to 7. Yep. And so on. this would map out this region right here. So mapping out these regions in 3 space is a little bit trickier. So now we set up our triple integral. And which one should come? I did my outermost, dx, 0 to 3. What should come next? Next innermost should be what? dy or z?
Y.
dy. And then this should be y equals. Now this is consistent. We're only going to have one variable. Remember when I set this up here? The outermost can have no variables. The next one can have at most one variable. And then 2 variables for the inner one. So y going from 0
To square root of 9
minus x squared, yep. And then dz is the innermost. And this is z equals. Now do you all do the same thing when you write z's? Do you put that line through the middle?
No, but I do put the crossbar for 7s.
Ah, okay. Why I put this line through the middle with my z is I've had plenty of times when my z's turned into 2's. And all of a sudden they're a 2 from then on. And I'm not totally consistent with making my 2's look like...
Fair.
Yeah. So, if I made my 2's with a curly at the bottom every time, I wouldn't confuse them, but I don't always do that. So z is from 0 to 9 minus x squared minus y squared. And there's the triple integral over this region. And if your f of x, y, z is 1, then you're going to get the volume of this region. Now, one of the new abilities you're going to get now is to take volumes of regions that we couldn't get with double integrals. And we can set up triple integrals now to get volumes of regions as well as double integrals. So we have a tool for finding volumes of regions. All right. Any questions on this before I move on?
So in this case, the function f(x,y,z), because it's not given, or it just this is the way we need to set it up, because the function itself is went up to as a boundary for z. So I don't know what's the function we have to start with.
Okay, so this we're kind of used to in double integrals, that the fxy was the thing that was always right here. In a double integral, the fxy was the surface that you were integrating under. But in a triple integral, the fxy z is something else. It can be, let's go over some of the possible applications again. It has nothing to do with the boundary that you're integrating on. The triple integral. This becomes a volume if fxyz is 1. It becomes a mass if fxyz is a density function, like pounds per square foot, or per cubic foot. And then we'd wind up, but if the density is constantly varying, you'd need a triple integral to get the mass of it. Okay? If f of x, y, z was a temperature, the temperature, so suppose you had a room where you had all these thermometers hanging from strings tacked into the ceiling. And so at all these different points, you had all these temperatures being reported to your computer, and you have a fire in one corner of the room, so there's very different temperatures. You freeze one instant in time and you get all the data. And then if you wanted to find the average temperature, you could do a triple integral at the bottom that would give you the volume, and then this is some kind of a volume but weighted by the temperatures, and when you divide them out you wind up getting the average temperature. And so this fxyz is something new in what we're working with. It has nothing to do with the boundary. In the double integral, the fxy was the upper part of the boundary. But here it's not part of the boundary. All right, any other questions? All right, let's go to this one. Now, many of the homework problems are, just find these triple integrals, kind of like we did this one. And they're kind of lengthy like this. Each one can take a while. But what I want to spend our class time on is making sure, because I think you can handle doing the triple integrals, the computational. What's harder to get a handle on is the concepts involved. So here's a problem that find the volume of the solid bounded by all of these. Now these are all surfaces. That's y equals 4 is a plane, z equals 0 is a plane, 3y minus 4z is a plane. This one is y equals x squared plus 2. Well, let's just kind of look at a visualization of this will be helpful. Y equals x squared plus 2. Now, if we were in the xy plane, we know that would look like this. Translating that over here is, so you go on the 2 on the y-axis, and then you have this. Parabola here. Now, there's no z in this, which means that you could put a plus 0z, which means z can be anything. So it goes straight up and straight down. So imagine this is like a sheet of paper that was set, you put the bottom of the paper on the xy plane like this, and you curve it, and so you've got these things going straight up. And then all these other planes, y equal 4, you only go out this far, meaning from here on we're not interested. So let me erase this part of the parabola. Now, the y equals 4, the x can be anything. And the Z can be anything, so it's a plane going straight up. A sheet of paper, if that's on the XY plane. Z equals 0. Now the X and the Y can be anything, so this is the XY plane. So XY plane, and then this other boundary, let's take this, move the Z to the other side, and let's solve for Z. Z equals 3/4 Y. Now, this is saying that the X can be anything. And let's just put this equation down. Now, this, when the Y is 0, the Z is 0. When the Y is 4, the Z will be 3. Now, you take this line up here, and you extend it, and we have a plane here. Now, the X isn't involved here, so the X can be anything. So we have this. Now, let me back up a little bit here. Okay. Now, what we're going to get when we put all this together is, you see, this plane is tilted up, and this paraboloid thing, parabola, and then that was going straight up. When we put this all together, we're going to wind up with something kind of like this shape. I'm going to draw it like this. We have this parabola. But the back side of it is going to be hidden from view, so I'll put it as dotted. And then we've got this. This is this parabola down in the XY plane. Now, we go straight up for a little while until we intersect with this plane that's on a tilt. And then that plane that's on a tilt is going to be intersecting with this sheet of paper that was this parabola shape that was going straight up. And so we're going to wind up with this. And this, since it was on a tilt, this is a little bit higher than this one. And we connect this over here. And then this, we come straight up from here, the same distance that this was up. And we connect these two. And then this is this portion of this parabola, but up higher on this plane, straight up from there, over here. Okay. Now, I happen to have a doorstop at our house. It's kind of shaped like this. It's kind of wedged down, it's kind of circular at the bottom, and it's kind of wedged angling up, and you stick it underneath the door to make the door not move anymore. And so, you know, the height from here is less than the height from the floor to the bottom of the door, and the height from here to here is more than the height from the floor to the bottom of the door, so that we know this will jam in there in the door. Alright, so can you all follow that this is the shape in here that's being carved out from all of this. Give me a little feedback in the chat. How are we able to follow this, or is it too hard to visualize this? Okay, and I wouldn't expect you to be able to come up with this shape on your own, but hopefully you can see as I'm drawing it that it makes sense. Alright. And might have to go over it again later, and just for that I'm going to put a little note over here. This parabola, this thing is in the XY plane. And while this other thing was tilted above the XY plane. Okay. And so now let's take this region. Now when we're finding the volume of this solid, I could go with a triple integral to do this. So the volume I can do a triple integral. Let's call the region D, and let's, if we make the fxyz to be 1, then this will give me the volume. And we have all these descriptions. So how can we put this together to make the set D? Well, these are going to be boundaries on X, Y, and Z. And the outermost one has to be just constants. There's got to be one with just constants. And anybody have a suggestion? Which one should be constants? X, the Y, or the Z?
Z.
Now, if we did the Z, it would go from where to where? Just
It
constants.
it would go from 0 to and then I'd have to solve for, and then I'd have to
Yes.
solve for the highest point of
That's
that
right.
that
You'd have
Y
to find
goes.
the highest point. So we could do it with Z, and the Z would be going from 0 to its highest point. Now, it's kind of a little bit arbitrary by just picking one of these, though. We could pick any of those to be the one.
Z would have to go from 0 to 12. No. It'd have to go from 0 to 3.
0 to 3, and how'd you get 3?
I find out how far Y goes, and then I plug in the Y value into the Z equals 3 over fourths Y.
So the biggest that Y can be is 4, plug that in and that's 12.
No, I plugged it into the modified expression. Z is equal to 3/4 y.
Sure. And then plug in the 4 there, and the 4's cancel out, and the z would go to 3. So we
Yes.
could be going from 0 to 3 for the z's, and then go from there. And that's a reasonable way to go about it. What I'm going to choose to do, though, is I'm going to go with the x's first. And the reason why I'm going to do that is because then if I look at the y's constrained by the x's, then I can go back to this 2D picture of x and y and get y in terms of x, and I'm very comfortable, and I'll be able to go pretty fast with that away. So I'm going to choose my x's to be the constants. When I have a choice, that's, if I can't see a good solid reason for anything else, that's what I'll do. Now, once in a while, let me just tell you, it'll depend upon the function itself, this fxyz. In this case, the fxyz is just going to be 1. But sometimes when the fxyz has a really nasty something in one of the variables, that might make a consideration of making that really nasty thing, like if it was just the z had all kinds of nastiness with it, then you might make that z be a constant relative to x and y for the integrals on this, and then have the z's. Then you only have to integrate that nasty thing once at the end, and then so there can be other considerations of which order which one you decide to make to be the constant ones. But when there's no other concerns, I like to do it like this. All right, now if this is the case, then what do my x's range from? Well, to find out what my x's range from, I got to find out this point right here and what it is right over here. Now, yes.
It ranges from 0 to 2 in order to fulfill the condition of y is equal to 4.
Now actually though, when x is 2,
Sorry.
x squared will be the 4 right here. Right.
No, in that case it would be the square root of 2. Sorry, it goes from 0 to the square root of 2.
Now, if we go from 0 to the square root of 2, we only get the one part of this. We have to go from negative square root of 2 to positive square root of 2. Okay, now if you went from 0 to square root of 2, that could be legitimate because of the symmetry involved. Because of the symmetry involved, we'd say we only have to find the volume of half of it and then double it. So that could also be the case. But if we're just going to set it up without doubling it, we're going to set it up like this. Now again, how I got the square root of 2 was I got to focus on this equation right here. And I know that the y is 4 when I'm at my maximum x. So I plug in 4 here, and then I solve for x. And subtract 2 from both sides, take the square root of both sides, you get plus or minus square root of 2. Okay, now if that's the case for my x's, then what do my y's range from? Now the y's range from this to this. From here, while x is a given value, like when x is 1, we go from here to here. When x is 1.5, we go from here to here, so on. So what are we ranging from? We're ranging from this, which is x squared plus 2, out to here, which is 4.
But shouldn't we be saying that the lower bound is 2 and the upper bound is x squared minus x squared plus 2 because we've got the x part of the triple integral sort of parameterized by the bounds?
I couldn't follow you. Start over.
Shouldn't we say that the bounds for y is from 2 to x squared plus 2?
From 2 to x squared plus 2?
Yes.
Okay. If we were doing that, that y equals 2 is this line right here. And this to here, you'd be getting this portion
Oh.
instead of this portion. If we go, because we got to go from left to right on this graph. If we're on this graph, it's up to 4. So it's from
So then
up to 4.
how about 4 minus x squared plus 2?
4 minus x squared plus 2.
As the upper bound.
And where'd you get this? 4 minus x squared plus 2.
No, that would give the area below all the way to the origin as well. I was hoping to try and create an area from which I'd subtract out x squared plus 2 in order to get the...
Let me zoom in on this.
The problem with 4 is that it would go all the way to the origin. So
We got to go from here up to here. So the y is stuck between x squared plus 2 and 4. Right there. From the lower limit to the upper limit. Yeah, this 4 minus x squared plus 2, that isn't going to work. Alright, so there's the restrictions on x. There it is on y. And now, if we just took the z between 0 and the highest height, which we said was 3, the problem with this would that this height would be the same as these heights. But this thing is sloping upward. So what we need to do is go z from 0 to, and here's the restriction on the z right here, which was the same as this right here, to 3/4 y. Okay. So putting all this together, we could say then that v is equal to the integral, the outermost one being negative square root of 2 to square root of 2. And then that's going to correspond with dx. And then the next one is y, so this is x equals y equals x squared plus 2 to y equals 4, and then there's a dy here. And then we have an integral, z equals 0 to z equals 3/4 y of dz, and we're choosing the f of x, y, z to be 1 so that we get a volume of this solid. And this is the triple integral that would represent the volume, and then we could execute this triple integral and we'd get a number, and that would be it. And that takes us through everything that I wanted to cover today. So the homework is this section 16.4. And any comments or questions?
I have a quick question, actually. So in this case, we just used a triple integral to find a volume, but I suppose we could have also used a double integral, and then the function could have just been the, like, plane. So are there any instances where you have a shape that is, like, arguably better to solve using a triple integral? Because I feel like this, like, it would have been easier using a double integral.
All right, what would we have done to get this as a double integral?
Well, what I would do is I would like I guess the base is this kind of semicircle, or it's not exactly a semicircle, but you know, it's
a known thing.
yeah, and then we could use the function that we would be, you know, using the double integral on could be the equation of the plane that kind of chops off the top of this shape,
Yes.
evaluated at, you know, z equals in terms of x and y.
That plane was z equals 3/4 y.
Yeah.
And then we would take our x and our y, and if we just used these, could that have done it?
I think so. Because I mean, when we integrate 1 and then evaluate it at 3/4 y, that's what we get anyways. So
That's right.
it's just like skipping a step, I guess.
If you did this very first one right here, so how does this, when you do this first one up here, you're just going to get the integral of 1 dz is z, subtract these limits, and you're just going to get 3/4 y, and this is going to be the next step when you do this integral, which is the same thing. So great question, Rowan, and it's showing us that this triple integral after the first step just becomes the same way we would have set this up to solve the volume problem as a double integral. Now, your other question was, are there regions where we'd prefer a triple integral to a double integral if we're just trying to find the volume?
May I
Yes.
try to answer that?
Go ahead.
Imagine if the lower z bound on the problem we just did, imagine if that had a y in it. Imagine if the lower bound of the z integral was z is equal to -3/4 y.
Okay.
Then we would need a triple integral to capture all of the
Very good. Very good. It's a double integral captures it from 0 on up automatically. But if this was something else other than 0, then we need the triple integral to get that. And another part of the answer to that, so excellent insight, Cameron. Another aspect of this, though, is that triple integrals usually are not used to find volumes. The much more common use of triple integral is something like to find the mass if you have a density function, or to find the average temperature within some region where you could say, all right, we'll weight this with temperature and then we'll divide out the volume and then we'll get the average weight, which is the average temperature. And so we kind of answered that a couple ways there. All right, anything else?
I have hopefully a quick after class question for you, Mr.
Okay, great. All right, good night for everybody else. And let me,
Thank you.
you're welcome. Stop the recording.